Hi. So this was work that was done at UCSB with Professor Wim van Dam. And if any of you are interested, this is the archive number. So to get into this, first off, I'm going to be talking about near-adiabatic computing. So let's just review the adiabatic condition a little bit and just get some language in here. So we're just going to be doing a basic evolution between two Hamiltonians. Right here I've listed a linear interpolation between them. Our results work with various different interpolation methods, so that's not exactly important. And I want to list here the adiabatic condition itself. So if you run your algorithm with a runtime that's much faster than some derivative of the Hamiltonian divided by the inverse spectral gap squared, you're going to run this adiabatically. And so we're going to look into ways to break that. What happens when you break this, when you run this faster? And I've listed this as a folklore condition. There are a few more rigorous versions of this, such as one by Lidar et al. Here. They all include the basic same ingredients of derivatives of the Hamiltonian inverse spectral gap. I've also wanted to put this up here because this quantity, which I'm calling rho, is going to come back later, and we're going to see this later in the talk. So, what do I mean by the near-adiabatic limit? Essentially, we're just going to run mostly adiabatically, but allow ourselves a little bit of leakage out of the ground state. So as we go, some of our state is going to leak into the first excited state. For the most part, we're going to ignore higher excited states. I've listed 30% leakage here. That's about as high as we've seen our results going and still being valid, but that's a fairly loose number. And essentially what we want to do is look at the probability of transitioning out of the ground state as a function of the total runtime that you take. So essentially, every point on this graph is its own annealing experiment. And we want to know, essentially, what determines this behavior. So just a brief outline of what I'm going to be talking about. I'm going to start with just a simple barrier tunneling model that I'm going to be using as an example. Even though that is an example, I want to state that our results are more general than just that model. I'm going to be using that for some numerical confirmation, but we think that our results should apply to other models as well. Then we're going to look at some previously known results when the gap is large, when you're following the adiabatic condition, and then get into our own results when the gap is small, when you're running this faster than you should be. So the model that I'm looking at is, again, just linear interpolation between two Hamiltonians. Your initial Hamiltonian is just a transverse field in the x direction on n qubits. And so the final Hamiltonian turns out to just be a function of the Hamming weight of your bit strings. So in terms of Hamming weight, your ground state is just going to be a binomial distribution in your Hamming weight. So essentially a binomial centered at n over 2, and then our final Hamiltonian is diagonal in the computational basis and depends on some function of the Hamming weight. And so the final ground state that we're looking for is the all-zero state, and to get there, this binomial distribution is going to have to tunnel through some barrier. Again, this is just an example I'll be using for numerical purposes. Our results are more general than this. And the model that we're using, depending on the size of that barrier, quantum adiabatic can take polynomial or exponential time. And our goal is going to be, again, to determine what this oscillatory behavior is as a function of your total runtime. And this really breaks down into two cases. One where you're following the adiabatic condition, and one where you mostly follow it, except maybe in a small region, an avoided level crossing or something like that. So let's first review the large gap case, where you're following the adiabatic condition, the gap is remaining large, you don't have any avoided level crossings, or if you do, you're going slowly enough through them. I do want to note that these results have been previously known. Lidar et al. In their proof of the adiabatic theorem do this. It's also been seen in several other results as well. And so we're essentially going to determine what this oscillatory behavior is. Some assumptions that we're making here that we'll also make in the small gap case are, first off, we're mostly staying in the ground state. So this C naught is the probability amplitude for being in the ground state, and we might allow some transition to the first excited state, and essentially the other excited states, we might transition to them a little, but we're going to ignore that for our purposes of approximation. And so the probability of transitioning out of the ground state is essentially going to be the probability of transitioning into first excited states. And here I've listed M as just the degeneracy of the first excited state. The barrier tunneling model that I showed before is n-fold degenerate in the first excited state, but non-degenerate in the ground state. We think that our methods will work for degenerate ground states as well. I'm not going to get into that too much during this talk, but that should work. Okay, and the previously known results are essentially that these oscillations, their frequency is entirely determined by the spectral gap, specifically the integral of the spectral gap over the course of your annealing schedule. In addition, we can fully determine this, so the solid lines are analytic approximations, and the dots on here are direct Schrodinger evolution data. And you can see that they mesh up exactly. So we're getting the frequency, the offset, the amplitudes, everything out of this. And Wiebe and Babcock have actually proposed using these oscillations as a way of timing your algorithm to specifically hit at appropriate times when the probability of transitioning out of the ground state is low. So, as we were going through and studying various problems, we noticed cases where this was breaking down a little bit, where you were getting more complex behavior out of this. And that occurs specifically when you're going through avoided level crossings and things. Specifically, you might see something that has more than one frequency in the oscillatory behavior. And so we want to determine what these other frequencies are, how to get them, why we're not just getting that omega is the integral of the spectral gap. And this is occurring specifically in cases where you're running faster than adiabatically through a small region. And we can actually predict most of this oscillatory behavior using the spectral gap itself. So it turns out that the point where the avoided level crossing is the point that you actually care about when you're determining what all these frequencies are. So here, this is just an example of what a spectral gap looks like in the barrier tunneling problem that I mentioned. So you're mostly having a large spectral gap, but then during some small region, you have an avoided level crossing. This might look like a Landau-Zenner crossing if you zoom in. It might have a different form. We've looked at a few different models and seen similar behavior from all of them. And it turns out that the location of that avoided level crossing in your annealing schedule is what fully determines what frequencies you're getting out of this and what behavior you're getting. So I brushed a little bit under the rug how you got that frequency in the original case. It turns out that it just depends on the endpoints of your spectral gap. This is the way that boundary cancellation methods work, if you're familiar with those. And the properties of the derivatives of the Hamiltonian and things like that are what determine what frequency you're going to get out of this, what kind of oscillations you're getting, all of that. And so we're going to ask, if we're running faster than through this, what is the next most likely point to contribute? And it turns out to be the avoided level crossing itself. There's some actual mathematical reasons for this. Rho, which is, again, that adiabatic condition parameter that I talked about, is becoming large. And in the math, that's actually coming into an oscillatory integral and becoming important. And that oscillatory integral also has a phase that's determined by the integral of the spectral gap. And if you're integrating the spectral gap through an avoided level crossing, it's almost stationary at that point. And so you can't use stationary phase approximation, but you're getting close. So it turns out that that point of avoided crossing is another point that matters when you're going too fast. And so you're going to get another contribution to the probability amplitude of being in the first excited state. And that additional amplitude is going to come in with a frequency omega plus, which when you take that over to the probability is going to give us now 3 frequencies. The original omega we had, which is the integral of the spectral gap over the entire evolution, and then an omega minus, which is the integral of the spectral gap before your avoided level crossing, and an omega plus, which is the integral of your spectral gap after your avoided level crossing. And so now we're dealing with 3 frequencies. As we go through this, we can see we're getting more than just these frequencies out of it. We're also getting things like what are the relative amplitudes of those oscillations, what are their phases, things like that. And furthermore, if we add in a little bit of information, say that this should look like a Landau-Zinner crossing, we can refine the theory a little bit more and use that to get a model that we can actually use to predict things. The model that we're using at the moment has a constant of proportionality that we need to fit. I'll get into a little bit what that causes and what that does and does not tell us. But basically, we can use this to predict those oscillations fully. And to give a brief example, here, the blue curve, blue solid line, is our model, the analytic approximation we're making, and the red dots are the direct Schrödinger evolution data that we get from simulations. And this is, again, for a barrier tunneling model. We've done this for other models as well, seen similar good results. And that constant of proportionality I stated says nothing about your frequencies or the phases of your oscillation. All it determines is what is the slope of this curve overall. So you can still, even without that constant of proportionality, figure out where the minima are occurring and when you should time your algorithm properly as you go. And to give a little bit more results, here I've listed the same results for the barrier tunneling model for various different values of n, the number of qubits. And you can see that as we go up in the number of qubits, we're getting less and less agreement. But the agreement that we're getting is still occurring at the same points. So you can still time yourself correctly. You can still find this minima at the same place. And the reason why these are all occurring at the same place is this is a similar barrier tunneling model, and the spectral gap looks similar for various different n as you're going up. And in fact, the only thing that's changing here is essentially how deep your Landau-Zinner crossing is going. And that is determining only how high up you're going. It's not determining anything about the frequencies or anything like that. And so we generally see that as our assumptions become worse and worse, as the probability of transitioning out of the ground state becomes larger, you're going to be getting less and less agreement, but you still can time things correctly if you want to. So just to conclude a little bit, the spectral gap here is determining everything. It's determining what the amplitudes of those oscillations are, it's determining what the frequency is, it's determining whether you should time your algorithm at specific points. We can even tell you whether this is going to be a large effect or a small effect in your system. Some things that we're still working on are whether you can get rid of that constant proportionality. We think it's related to how this isn't an ideal Landau-Zenner transition, and also just how feasible this would be to see in an actual system. So, any questions you have, can take.
Thanks, Lucas. We definitely have time for a few questions.
Yeah, hi. I'm wondering, I think it's following up on your own question here, the bottom one there. Can you say anything about the computation time to compute the oscillatory behavior and the location of the best place to slow it down? And is that slower than the actual anneal time?
So that, the actual computation, what you really need is just the spectral gap. You don't actually need to know how small the spectral gap gets, though, just where it gets small. So depending on your problem, that might be easy or hard, but you are still running into the same problem of you need to know information about the spectral gap beforehand here. We do think that if you got some data at maybe some parts of a system, at some runtimes, you might be able to do a Fourier analysis of it to figure out what these frequencies are a posteriori and use that to time later cases. But again, you need to know something about your system.
Two questions. One is how easily does this generalize to having more than one small gap? And the other one is have you thought about generalizing this to Lindbladian evolution, where the relevant gap is the gap of the Lindbladian rather than the Hamiltonian?
To answer the first question, very easily. You get the exact natural extension that you would think of if you add in another Landau-Zenner crossing, you split your frequency again right around that crossing. For the other one, we've thought about that a little bit, but haven't done any work on it. We do know that that would be the natural next extension, but we haven't actually looked into that yet.
So I was wondering about this free parameters. You had one free parameter. Is there a physical interpretation what this is?
Is there a physical...
what this free parameter is, physically?
Essentially, we think that it's related to how close the crossing is to an actual ideal Landau-Zenner. We're not sure about what exactly is going into that, and we've taken some look and are still trying to figure it out.
So like the curvature?
The curvature, how long you're actually in that, how much the higher excited states are contributing, since Landau-Zenner is a two-state system.